Okay, good evening everyone, and sorry for the delay. Technical problems and sometimes airplanes cause problems. We have a talk here. I will do the introduction real quick. This is Christine Gorbet. She's an MIT student and she does research on artificial intelligence. You all probably have had problems with translation, automatic translation systems, and she will actually tell you a little bit more about that. Welcome.
Can I have you? Oh, here we go. That does indeed work. It wasn't working before. Okay, welcome everyone. Sorry about all the technical problems. They, of course, lost my luggage at the airport, which meant I get to use a fun little Windows laptop here. It's all in German. German's a good language, but I needed the machine translation to help me out with the menus there. So I'm Christine Corbett-Moran. I'm from MIT in the US, and I work in the computer science and artificial intelligence lab there. And today I'm going to talk to you about open sourcing machine translation. I'm going to give you a little bit of history of the machine translation movement, tell you where we've been, some different approaches, and I'm specifically going to focus on statistical machine translation and present an open source toolkit that's available now on SourceForge for statistical machine translation called Moses. So let's get started. History of machine translation. It was one of the first applications conceived for computers. IBM exhibited simple word-to-word translation system in as far back as 1954, and we had some early optimism here. It will not be very long before the remaining linguistic problems in machine translation will be solved for a number of important languages. We're still waiting on that, actually. This is 1958. So these early approaches, like a lot of other AI research, MT is actually referred to as an AI complete problem. Like a lot of these other AI complete problems, there was a lot of early optimism that sort of fizzled out. And these early approaches really failed to scale to back up such optimism. And here we have a US government report that was just very, very negative, and kind of quelched any research in the field for almost a decade. So we do not have useful machine translation, and there's no immediate or predictable prospect of useful machine translation. So we're working to change that still today, and machine translation is useful for a number of applications. Here's the State of the Union. There was a resurgence after this negative report. There was a resurgence in the 1980s that was mainly rule-based approaches. So if you have all these PhD linguists writing rules for machine translation systems, you can, for certain language pairs, if you hire a lot of linguists, you can get some pretty good output. The disadvantage is it requires a lot of man hours, lots of researchers, so it's only applicable to people who want to invest a lot of money into a certain language pair. So if you wanted to build a machine translation between Finnish and German, then you're not going to have the money to back that unless you're Bill Gates and for some reason there's a war between Finland and I don't know, Germany or Greece or whatever, then you'll back that. But otherwise, these people who want machine translation systems in other languages are just going to lose out. There was another resurgence in the 1990s, the IBM noisy channel model, and I'll explain this term later, but for now, let it just stick in your mind, paved the way for statistical systems with heavy engineering components, and that's some math I'm going to talk about later. And this is where we're really at today. In 2000, we're kind of merging these two approaches, merging the rule-based approach by automatically generating some rules, incorporating more syntax, with the statistical approach that really dominated the 1990s. And we're still working on this today because MT is hard, machine translation is hard. You have all this stuff going on in language, sense, order, tense, idioms, ambiguities, reference. If you're not a native English speaker, I'm probably speaking too fast for you, for example. But all these things going on in language make it hard. And the amount of data required for a good machine translation system that's not manually written by people's data in their head, which is a lot of data as well, it's very, very large. You need words, you need phrases, syntactic information, and in addition, it has to be as consistent and correct as possible, because if you have inconsistencies, you're not going to get a good output there. So that's the state of the union today. And the bar is really high for machine translation systems. As a human, you can be very critical because you're probably better than any machine translation system. I'm going to be honest here, it's going to be in the next 20, 30 years at least, just by the time you're 8 or 9. So the bar is very, very high. You want something that's general purpose, not limited to, say, making a flight, but something that can translate any sort of domain of interaction. You want it to be human quality, just the tiniest thing that's off will really stick in your mind, and automatic, so you don't want to hire all these linguists to generate these systems. The demand is very high for a few language pairs, English to Arabic, or English to Spanish, or between different European Union countries, there's a high demand. But adequate MT for most language pairs, still non-existent. Here's some sample output. I'm not going to read this all here, but you can sort of see the output is right here, and it's adequate. This is one of the better MT systems. Through petition received by the Inter-American Commission on Human Rights hereinafter on 6 October 1997. So I missed a couple things. This should be hereafter. October 6th, though we can parse that, maybe we want to switch those two, and petition probably needs an article like the or a or something like that. But you can parse it, so it's getting close. So again, I talked about all these demands for MT. You have the European Union, where in the European Union, it's by law, in the parliament, you have to translate important parliamentary documents between all pairs of official languages of the EU. So if you study complexity theory at all, you add another country, that adds another entire all pairs sort of situation. So that, I mean, that in itself, the EU really invests $1 billion a year, at least, in humans translating. So even MT, if it's not perfect, if it can help a human translator do their job more quickly, get them started, then that's another application. And the US government and military, as well as other militaries, employ scores in intelligence translation. And translation, this is where I'm at right here. Translation renders information a wider net of accessibility. If you have a document that you want to write in German, that you want to write in whatever your native language is, if that document exists, whether it's documenting source code, whether it's your personal blog, whether it's a user manual for something, that should be accessible to anyone, whether or not that's their native language. So one of Google's most important assets is their growing machine translation suites. They use a rule-based system, more of the 1980s approach that's very functional but limited, which is why you don't see all language pairs on Google's translation engines, but they're transitioning to the statistical methods for some of the newer and up-and-coming languages like Arabic and Chinese, and they're using methods very similar to those I'm describing today, but a little bit more closed source and proprietary. So here we go. This is our goal, sort of, to climb this triangle. Here you have foreign words and source words. The easiest approach to translate is just do it word by word. But if you can imagine, I'm sure you've done this with your favorite new language that you're learning, it ends up a little funny. So that doesn't end up quite right. But you can do this in more sophisticated ways and approach it in a statistical method and actually generate some good output. The syntax to syntax, imagine if you've ever done sentence diagramming in school, marking things with verbs and nouns, and whether it's a subject or an object. If you were to do that in both languages and then generate automatically or with linguists a few rules to translate one sentence diagram to another sentence diagram, we actually call them trees, but it's the same sort of concept. Then you could really work on this level. This is a little far off, maybe psych or some sort of knowledge semantic database using WordNet or something like that. You could translate semantics, meaning. And some approaches actually try an interlingua. They posit that we could use an intermediate language as sort of an interface between all different languages. And then you don't have to do all pairs. In the EU example, you could translate Finnish to the interlingua, and then from the interlingua you'd have a translation to any other language. So that saves a little bit. So this I just went over in that diagram, which was a little more clear, but you can do word-to-word, syntactic, interlingua, and statistical sort of is now incorporating all these, trying to climb this tree, and coming up all the gory details. Much of the state-of-the-art theory was proposed by IBM in the early 90s, and the goal is to find the most probable target sentence given a foreign sentence. So you're going to try to translate from this foreign language to a target language. A lot of the convention in the literature is to call the target language English or E. You can make up something that's not so Anglo-centric, but IBM, I guess, was very interested in translating into English, so most of the time they'll refer to the target language as E and the foreign language as F. Now the basic idea is to use parallel corpora to automatically align words and sentences deriving probabilities. Now what are parallel corpora? If you have two texts that express the same thing, maybe translations of each other, then you can use algorithms to align the sentences. Say this sentence says the same thing as this sentence. And when you have these two sentences that say the same thing, you can derive statistics about that. If you align the words and the phrases, you can say this phrase aligns to this phrase 50% of the time, and this phrase aligns to another phrase the other 50% of the time. And I'll show you a table that'll probably make more sense. This requires a really large amount of data, which is still viable for a limited number of language pairs. We have this data for the European Union that in their parliamentary sessions, as I mentioned, translate lots of parliamentary documents between all language pairs. So given all this data that's human generated, we can learn from that and then do our own statistically generated machine translations. So here we're going to go, I'm going to go through a bit of math here. This is just to get the symbols a little sticky in your head, and then I'm going to actually go through this in more detail and come back to this slide. So given a foreign sentence F, we're looking for the English sentence or the target language sentence that maximizes the probability of the English sentence given the foreign sentence. That's this notation here. This will give you the English sentence which yields the highest value for this probability. And this is statistically the most likely translation. And hopefully, if you've trained your system well enough, this is the best translation, the most likely best, if you have enough data and very good data. So we can generate this in a sort of easy manner. If we have, this is the table I was mentioning, translation pairs in a parallel corpus. So here I have maybe, what if I have the same children's book in two different languages? In one language, French, it says "Je mis mon chat," or however you say it in the best French accent, which can either translate, in our children's book, it translates two different ways. The translator picked, "I like my cat" once, and "I love my cat." I like my cat 7 times, and I love my cat 3 times. So then, the probability of translating "Je mis mon chat" as "I like my cat" is 70%. So here in this little children's book example, we would pick "I like my cat" as the translation. So this is for a small amount of data, and I'm going to sort of go through these necessary math, a little bit of math. It's not really that hard, it's just more notation. So P of E is the a priori probability, and if E is the English string "I like pizza," then P of E is the chance that a certain person at a given time will say "I like pizza" as opposed to saying something else like "I like ice cream" or "thank you" or any other thing. So you might think, how do you find this? We'll talk about that a little later, but one way that you can approximate it is something like the web. If we have all the documents on the web in English, we can say that people maybe often say "I like pizza" and not so often say "I like Brussels sprouts" or "I love George Bush" or other great things like that. So you can, if you have the total number of things that are said, then you can sort of derive a probability from that.